planet orbits the Sun every 165 years, has 14 moons named after nads, is battered by supersonic winds, and has only ever been photographed from close range by a spacecraft once. Neptune, the third largest planet in the solar system after Jupiter and Saturn, hardly appears in our solar system's family photo albums. That's despite the fact that Triton, its moon, is virtually covered by a liquid ocean. It's been nearly 33 years since NASA's Voyager 2 spacecraft flew close enough to Neptune, giving humanity its first and only close encounter with the planet. Scientists were astounded when they saw the first true photos of Neptune, thanks to the Voyager 2 spacecraft and Hubble Space Telescope. But what did they see, and how will it affect you? Let's find out. Neptune, the eighth and farthest planet from the Sun, is a gorgeous blue sphere named after the Roman god Neptune. Pluto once held this distinction. However, the International Astronomical Union downgraded Pluto from its status as a planet. Neptune, which is over 3 billion miles from the Sun, orbits the Sun once every 165 years. Thus, it hasn't quite completed a full cycle around the Sun since it was discovered. Known as a gas giant, Neptune is one of 4 planets outside the asteroid belt, including Jupiter, Saturn, and Uranus. These planets have a diameter of 4 to 12 times that of Earth. They have no solid surfaces but vast atmospheres containing significant volumes of hydrogen and helium, as well as traces of other gases. Neptune is the smallest gas giant in our solar system, with an equatorial diameter of 3,775 miles. That's not to mention the fact that it could house roughly 60 Earths in volume. Neptune is the only large planet that requires a telescope to see. As bright as the faintest stars visible to the naked eye, it has an apparent magnitude of 7.8. As a result, it is safe to assume that Neptune had never been observed before the invention of telescopes. Over the last few years, Earth-based telescopic studies of Neptune have revealed intriguing hints of dynamic cloud structures on the faraway planet, allowing scientists to estimate the speed of the planet's rotating winds. In this context, Voyager scientists prepared for the first encounter with Neptune, possibly the only close-up look at Neptune many of us would ever get. NASA's Voyager 2 became the first spacecraft to see Neptune, its last planetary target, in the summer of 1989. Voyager 2 made its closest approach to any planet since leaving Earth 12 years ago, passing nearly 300 miles above Neptune's north pole. Voyager 2 passed around 2,500 miles from Neptune's largest moon, Triton, 5 hours later. Scholars and scientists alike were obliged to re-evaluate their understanding of the solar system's large planets as a result of what they discovered. The planet's blue tint, caused by the abundance of methane in the atmosphere, is the most noticeable feature in Voyager images. The longer wavelengths of sunlight are more easily absorbed by methane. Colors on the blue end of the spectrum are the only ones left to be reflected. Even though Neptune receives only a third of the amount of sunlight as Jupiter, it is nonetheless a lively planet. Jupiter's hurricane-like storms can be seen as several big dark blotches on the surface. The largest of these spots is enough to contain the entire Earth. The storm size was estimated at 8,000 by 4,100 miles, making it similar to Jupiter's Great Red Spot. Originally, it was speculated to be a vortex. In 1989, the Voyager 2 spacecraft captured a shot of Neptune's massive anticyclonic storm. The feature, which the discoverers named the Great Dark Spot, appeared to be an anticyclone comparable to Jupiter's Great Red Spot. The Great Dark Spot on Neptune is equivalent in size to Jupiter's Great Red Spot and is located at the same latitude. On the other hand, the Great Dark Spot on Neptune is significantly more changeable in size and shape when compared to its cousin Jupiter. The bright, wispy cirrus-type clouds that cover the Great Dark Spot's southern and northeastern edges could be akin to the lenticular clouds that occur above Earth's mountains. A brilliant, irregularly shaped, eastward-moving cloud orbits Neptune at around 42 degrees south, moving more quickly than the Great Dark Spot, scooting about Neptune in roughly 16 hours. It's possible that this scooter is a cloud plume ascending between cloud decks. Voyager scientists have designated a second region known as D2, south of the Great Dark Spot. The heat radiated by Neptune's atmosphere was also measured by Voyager above the clouds. The atmosphere is hotter at the equator, cooler in the mid-latitudes, and warm again near the South Pole. It's also remarkable that the polarity of Neptune's magnetic field is the same as Jupiter's and Saturn's but opposite that of Earth. In addition, Neptune's magnetic field provides further insight into the planet's structure and dynamics. The Voyager discovered auroras in Neptune's atmosphere, which are identical to Earth's northern and southern lights. Electromagnetic radiation from the Earth's magnetic field lines causes auroras on Earth. This convoluted magnetic field makes it possible for the auroras to occur over large areas of Neptune rather than simply around the planet's magnetic poles. On Neptune, the auroral output is predicted to be around 50 million watts, compared to 100 billion watts on Earth. Unlike the other frozen satellites Voyager has explored, Triton's size sets it apart from the others. An orbit of Triton around Neptune takes 5.87 days, with an average distance of 205,000 miles above the planet's cloud tops. Triton is about 3/4 as large as Earth's moon, and it travels in a tilted, circular, retrograde orbit. Voyager 2 images show active geyser-like eruptions shooting out nitrogen gas and dark dust particles many kilometers into space, showing Triton to have a fascinating geological history. Approximately 1,680 miles across, Triton has a diameter of 2.66 grams per cubic centimeter. This suggests that Triton's interior is more rock-rich than those of Saturn's and Uranus' icy satellites. Triton's high density and retrograde orbit both point to it being a captured object, not something that formed in the vicinity of Neptune. Tidal heating may have warmed Triton in its originally eccentric orbit, and the satellite may have remained liquid for up to 1 billion years after being captured by Neptune. If this is the case, Triton's history is still a mystery, but volcanism is undoubtedly a part of it. At -235 degrees Celsius, Triton is the coldest place in the solar system. To comprehend what is taking place on Triton, one must first ask, what is the definition of cold? What is the definition of softness? What is the definition of youth? Water ice, with a melting point of 0 degrees Celsius, deforms more easily and quickly on Earth than rocks. But at the extraordinarily cold temperatures observed on Triton, more than 4.5 billion kilometers from the Sun, it becomes virtually as hard as rock. Because nitrogen and methane ice are too soft to hold much of their own weight, the majority of the geologic formations on Triton's surface are most likely made of water ice. At fewer than 100 degrees above absolute zero, nitrogen and methane, which constitute a thin veneer on Triton, convert from ice to gas. The nitrogen and methane on Triton are responsible for the majority of the geologically recent eruptions. At very low cryogenic temperatures, Voyager images of many geyser-like volcanic vents, which appear to be spewing nitrogen gas coated with extremely small black particles, showed evidence of such eruptions. To reach Triton's surface, the particles must first be lifted to heights of 1 to 5 miles in the air, where they are then blown downwind for some time. Scientists had hypothesized about the existence of incomplete rings or ring arcs around Neptune. Most agreed that shepherding satellites would herd ring particles between them, preventing them from either escaping into space or falling into the planet's atmosphere. This theory explains certain novel occurrences seen in Jupiter's, Saturn's, and Uranus rings. A ring-like pattern was captured by Voyager 2's cameras as it approached Neptune. A closer examination of the images revealed that the rings do indeed extend all the way around the planet, thanks to enhanced resolution and computer processing. Earthbound astronomers were unable to detect the full rings because the rings are so diffuse and the material in them is so fine. It's now been determined that one Earth-based ring arc observation was caused by the transit of a tiny satellite through the ring area. According to Voyager's discoveries, researchers were able to determine the number of rings and a tentative nomenclature late in their encounter. The surface of Neptune differs significantly from that of Earth. The surface of the planet is covered in thick clouds, but the planet's interior is filled with dense, pressurized gases, rock, and ice. Rock and ice make up the majority of the interior. One can't really tell what the prospects for Neptune and its satellites are in the future. Thanks for watching another episode of Space Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.